Somewhere out in the depths of space, astronomers pointed the Hubble Space Telescope at a patch of sky and found something that shouldn't technically exist according to anything we've ever cataloged before. No glowing stars, no familiar spiral arms, nothing that looked like the thousands of galaxies already sitting in Hubble's own archive. Just an enormous, quiet cloud of gas, sitting alone in the darkness with no stars inside it at all, and yet weighing in with enough gravitational pull that something invisible had to be holding it together. And when the team finally worked out what they were actually looking at, they realized they'd stumbled onto an entirely new category of object, something the universe has apparently been hiding in plain sight this entire time. And they nicknamed it Cloud 9. And in this video, I want to walk you through exactly what Hubble found, why astronomers are calling this one of the more genuinely significant discoveries of the year, and what it might mean for one of the biggest unanswered questions in all of cosmology. So let's start with the basics, because to understand why this discovery is such a big deal, you first need to understand what astronomers normally expect to find when they look at a young galaxy forming somewhere out in the universe. When galaxies form, the standard picture looks something like this. Gravity slowly pulls together enormous clouds of hydrogen and helium gas left over from the early universe, and as that gas collapses inward under its own weight, it eventually gets dense enough and hot, enough to ignite nuclear fusion, and stars are born, and over time, those stars cluster together, gas continues falling in, and you end up with the kind of galaxy we're familiar with. A busy, glowing structure absolutely packed with stars. And this process has played out an almost unimaginable number of times across the history of the universe, which is exactly why finding something that breaks that pattern entirely is such a genuinely strange and exciting moment for astronomers, because what the team studying Cloud 9 found was a massive, genuinely substantial cloud of gas, rich in the raw material needed to form stars, sitting out in space completely on its own, with absolutely no stars inside it at all, not a few scattered faint ones, not a small cluster tucked into a corner, none. And that alone would be strange enough. A leftover pocket of primordial gas that simply never got around to forming any stars, but here's where it gets genuinely puzzling. When astronomers calculated how much this cloud actually weighs, based on how it's moving and how it's gravitationally interacting with its surroundings, they found it has far, far more mass than the gas alone could possibly account for, meaning something invisible, something that doesn't emit or reflect light in any way we can currently detect, has to be sitting inside or around this cloud, providing the additional gravitational pull needed to hold the whole structure together. And that invisible extra mass points directly toward dark matter, the mysterious substance that makes up roughly 85% of all the matter in the entire universe, and that astronomers have never been able to directly observe, only infer from its gravitational effects on the things around it. And it's worth taking a moment to actually explain why scientists are so confident dark matter exists at all, even though nobody has ever directly detected a single particle of it, because that background genuinely helps make sense of why a discovery like Cloud 9 matters so much. The evidence for dark matter comes from several completely independent lines of observation that all point toward the same basic conclusion. Galaxies rotate far too quickly at their outer edges to hold together based purely on the gravity of the visible stars and gas we can actually see within them, meaning something extra and invisible has to be providing additional gravitational glue. Galaxy clusters bend and warp light passing through them, a phenomenon called gravitational lensing, far more dramatically than their visible mass alone could account for. And detailed measurements of the faint, ancient radiation left over from the Big Bang itself, called the cosmic microwave background, consistently show a universe whose overall structure only makes sense if roughly 5 times more matter exists than what we can actually observe directly through light. And all of these independent lines of evidence converge on the same basic picture, that the vast majority of the universe's actual matter is invisible to every instrument we currently have, interacting with the universe almost exclusively through gravity rather than through light of any kind. And this is exactly why the research team ended up describing Cloud 9 as a genuinely new type of astronomical object. Not a variation on something we already knew about, but a distinct category that had never been formally identified and confirmed before, a starless, gas-rich, dark matter-dominated cloud, essentially a fossil, a relic left over from the very earliest stages of galaxy formation, sitting frozen in a state that never actually progressed to the point of forming stars at all. And I think it's worth pausing here to actually explain why that specific combination is so scientifically significant, because astronomers have long theorized, based purely on computer simulations and mathematical models of how galaxies should form, that objects exactly like this should theoretically exist. Small pockets of gas and dark matter that, for whatever specific reason, gravitational conditions weren't quite right. Environmental factors interfered. Some structural quirk in how the gas was distributed simply never crossed the threshold needed to actually ignite star formation. And these theoretical objects have sometimes been referred to as dark galaxies or failed galaxies in earlier scientific literature. Essentially galaxies that got most of the way through the recipe but never finished baking. And it's genuinely worth understanding that astronomers have actually gone looking for objects matching this general description. Over the past 2 decades, several previous surveys using radio telescopes specifically searched for concentrations of hydrogen gas without any accompanying starlight, hoping to catch exactly this kind of dark galaxy candidate. And a handful of promising candidates did turn up over the years, but in nearly every previous case, follow-up observations eventually revealed a faint previously undetected stars hiding within the gas, meaning the object wasn't actually starless after all. It simply contained stars too faint for the original survey to have picked up. And that repeated pattern, promising candidate, followed by eventual disqualification once better data came in, is exactly why confirming Cloud 9 as a genuinely starless object required such an unusually careful, thorough observational approach, and why its confirmation carries so much more weight than an initial, unconfirmed candidate detection would. But here's the thing. A theoretical prediction sitting in a simulation is a completely different thing from an actual confirmed detection out in the real universe, and until this specific discovery, nobody had ever definitively found and confirmed one of these objects observationally, which is precisely why Cloud 9 matters so much. It's the first time this long-predicted category of object has actually been caught and confirmed, moving it from a theoretical possibility that computer models suggested should exist to a genuinely observed, documented reality that astronomers can now study directly. And I think it's worth walking through exactly how the research team actually found and confirmed this, because the detection process itself is genuinely clever and worth understanding. Spotting a cloud that emits essentially no light of its own is an enormously difficult observational challenge, since most of the tools astronomers use to study distant objects rely specifically on detecting light, whether that's visible light, infrared, radio waves, or some other part of the electromagnetic spectrum. And a cloud with no stars inside it simply isn't producing much light for any telescope to directly pick up on its own. So instead, the research team had to rely on a combination of indirect detection methods, looking specifically for the faint signatures of hydrogen gas itself, which can be detected through very specific wavelengths even without stars lighting it up from within, and carefully studying how the cloud's gravity was subtly influencing and distorting light from more distant background objects passing near or through it, a technique related to the broader concept of gravitational lensing, where the mass of an object bends and warps the path of light traveling past it. And it's worth understanding that a huge part of this kind of research actually involves systematically ruling out more mundane, boring explanations before landing on something as genuinely novel as a new category of object. And the research team behind Cloud 9 had to carefully work through and eliminate several more conventional possibilities. First, could this simply be an ordinary gas cloud whose mass had been slightly overestimated due to some kind of measurement error or unusual gas density? Could it be a normal, ordinary galaxy that simply happened to contain extremely faint, hard-to-detect stars that the telescope's instruments had somehow missed, rather than a genuinely starless structure? Could the apparent extra mass actually be explained by some foreground or background object happening to sit along the same line of sight, creating a misleading illusion of extra gravitational influence that wasn't actually coming from the cloud itself at all? And it was only after carefully working through and ruling out each one of these more conventional explanations, using multiple independent observations and cross-checks, that the team felt confident enough to conclude they'd genuinely found something new. And that kind of careful, methodical elimination process is exactly what separates a credible, peer-reviewed scientific claim from a premature, attention-grabbing announcement. And by carefully combining these different indirect lines of evidence, the team was able to build up a genuinely convincing case that this cloud existed, that it contained a substantial reservoir of star-forming gas, and critically, that its total mass, calculated from its gravitational influence, was considerably higher than the visible gas alone could account for, pointing directly toward a significant hidden component of dark matter holding the whole structure together. And Hubble's specific role in all of this was genuinely central, because Hubble's exceptional sensitivity and its ability to observe extremely faint objects with high precision made it possible to actually gather the kind of detailed, careful data needed to distinguish this object clearly from ordinary background noise or observational error. And boy, it's genuinely worth understanding a bit more about Hubble's own history here, because it adds real context to why a discovery like this one still carries so much weight. Even decades after launch, Hubble was launched into orbit back in 1990, and famously, its very first images came back blurry due to a manufacturing flaw in its primary mirror, a problem that NASA astronauts actually fixed through a dramatic space shuttle servicing mission back in 1993. installing corrective optics that finally allowed, like the James Webb Space Telescope, when in reality, Hubble continues making genuinely original, significant contributions to astronomy, specifically because of its unique observational capabilities and the sheer accumulated depth of its archive, built up over so many years of continuous observation. And I want to spend a moment on why this discovery genuinely matters beyond just being an interesting curiosity, because it actually connects directly to some of the biggest open questions in modern cosmology. First, it offers astronomers a genuinely rare, real-world laboratory for studying dark matter in a comparatively simple environment, and the specific advantages worth dwelling on a bit further. Because one of the persistent challenges in dark matter research has always been separating dark matter's gravitational fingerprint from all the other messy, competing gravitational influences present in a typical galaxy. The pull of billions of individual stars, the churn of gas and dust, the complex effects of supernova explosions reshaping a galaxy's structure over time. All of that activity essentially adds noise on top of whatever signal dark matter itself is producing, making it genuinely hard to isolate cleanly. But a cloud like Cloud 9, with no stars and comparatively simple internal structure, offers something closer to a controlled laboratory environment by cosmic standards, where the gravitational signal from dark matter isn't competing with nearly as much surrounding astrophysical noise, potentially allowing for considerably more precise measurements of exactly how dark matter is distributed and how it behaves gravitationally, without needing to first untangle it from a much messier, star-filled environment, because most of the places astronomers typically study dark matter inside galaxies within galaxy clusters are also filled with stars, gas, dust, and all sorts of other complicated, messy astrophysical activity that can make it genuinely difficult to cleanly isolate dark matter's specific gravitational effects from everything else going on. But a starless cloud like Cloud 9 strips a lot of that complexity away, giving researchers a comparatively cleaner environment, specifically for studying how dark matter behaves and distributes itself without the usual interference from stellar activity. Second, it offers a genuinely valuable case for our broader theories of galaxy formation, because if these starless, gas-rich, dark matter-dominated clouds really do represent frozen, unfinished stages of galaxy formation, then studying Cloud 9 in detail could help astronomers better understand exactly what specific conditions are actually required to successfully tip a cloud of primordial gas over into forming stars, and conversely, what conditions cause that process to stall out or fail entirely, which is a genuinely important piece of the broader puzzle of understanding how the countless galaxies we do see scattered across the universe actually came to exist in the first place. And third, and this is honestly one of the more exciting implications for the field going forward, if Cloud 9 really does represent a previously unrecognized ray of object, that raises a genuinely interesting question about just how common these things might actually be scattered throughout the universe. If this is truly the first confirmed detection of an object type that theoretical models have long predicted should exist, it's entirely possible that similar starless, dark matter-dominated clouds are sitting out there in significant numbers, simply never having been noticed before now, specifically because they don't emit the kind of light that traditional survey methods are built around detecting. And if that turns out to be the case, it could meaningfully reshape how astronomers approach the broader challenge of accounting for all the matter, especially dark matter, believed to exist throughout the universe. And I think it's worth being appropriately careful and precise here. Two, because this is genuinely one confirmed detection of an object exactly matching this specific profile. And as exciting as that genuinely is, rigorous science generally requires independent confirmation and additional examples before a newly proposed category of object becomes fully, broadly established within the field. So the realistic, honest next step here involves astronomers actively searching for additional candidate objects matching this same general profile, using both Hubble and other available telescopes, to determine whether Cloud 9 really is the first confirmed example of a genuinely common, previously overlooked type of object, or whether it represents something considerably rarer and more unusual. And that specific follow-up process, searching for more examples, comparing their properties, refining the theoretical models based on what's actually found, is exactly how this kind of discovery typically gets built out into a fully established, broadly recognized area of astronomical study over the following months and years. And it's worth mentioning that this Cloud 9 discovery hasn't been the only genuinely significant Hubble finding making headlines this year either, because 2026 has actually been a remarkably productive year for the telescope across several completely different areas of astronomy. And I think briefly touching on a couple of these helps illustrate just how much active, ongoing scientific work continues to come out of this specific instrument, Earlier this year, in July, a separate team of astronomers using archival Hubble data combined with additional observations from the newer James Webb Space Telescope finally managed to locate a specific stellar mass black hole sitting inside Omega Centauri. And it's worth understanding a bit about what makes Omega Centauri itself such a genuinely fascinating target for this kind of search in the first place. It's the largest known globular cluster orbiting our own Milky Way galaxy, containing roughly 10 million stars packed into a comparatively small, dense, spherical region of space. And some astronomers have even speculated that Omega Centauri might actually be the stripped-down remnant core of a much smaller galaxy that our own Milky Way absorbed and consumed billions of years ago, rather than an ordinary star cluster that formed the way most globular clusters do. An enormous, densely packed cluster of stars that has genuinely puzzled astronomers for decades. Because based on how many stars exist within that cluster and how old it is, theoretical models have long predicted it should contain a substantial population of black holes, remnants left behind by exploding stars over billions of years. And yet, direct evidence for those black holes has remained frustratingly scarce. And finally, locating and confirming even just one of these long-predicted black holes represents a genuinely important step toward better understanding how black holes actually form and behave within dense stellar environments like this one. And separately, back in June, another Hubble research team found something else nobody was specifically expecting: ultraviolet light coming from a galaxy that existed just 1.4 billion years after the Big Bang, an almost impossibly early point in the universe's history. And that galaxy turned out to contain tightly clustered young stars producing enough intense, ionizing light to actually transform the surrounding neutral hydrogen gas around it, clearing away what's often described as the neutral cosmic fog that once filled the early universe. And that specific finding is helping astronomers better understand exactly how and when the early universe transitioned from being largely opaque and foggy to the clear, transparent state we observe stretching across space today, a genuinely fundamental question in cosmology, sometimes referred to as the era of Ryanization. And I mention both of these additional discoveries specifically because they help paint a fuller, more accurate picture of what Hubble has actually been doing this year. This isn't a telescope quietly coasting along on decades-old reputation. It's an instrument that, even more than 35 years after its original launch, continues to produce genuinely novel, scientifically significant findings across multiple completely different areas of astronomy simultaneously, from confirming an entirely new category of dark matter-dominated object, to finally locating long-predicted black holes inside a famous star cluster, to catching ultraviolet light from one of the earliest galaxies ever observed. And I think that's honestly one of the more remarkable, underappreciated aspects of this entire story. Hubble was launched back in 1990, and rather than being fully retired or rendered obsolete by newer instruments, it continues operating as part of a genuinely productive, complementary partnership with the James Webb Space Telescope specifically, with Webb's exceptional infrared capabilities, allowing it to peer through cosmic dust and observe extremely distant, faint objects in ways Hubble simply can't match, while Hubble's own particular strengths in visible and ultraviolet light continue to provide genuinely unique, irreplaceable data that Webb isn't actually designed to capture on its own. And this kind of complementary, multi-observatory approach, where different telescopes each contribute their own particular strengths to build a more complete picture of a given discovery, is becoming an increasingly common and genuinely powerful pattern across modern astronomy, exactly as we saw with the Omega Centauri black hole discovery, specifically combining both Hubble and Webb data together to reach its conclusion. And I think, stepping back, the genuinely exciting, honest takeaway from the Cloud 9 discovery specifically is this: astronomers just found direct observational confirmation of an object type that had, until now, existed only as a theoretical prediction inside computer simulations, a starless, gas-rich cloud held together by an invisible scaffold of dark matter, frozen at what appears to be an early, unfinished stage of galaxy formation. And this single discovery opens up a genuinely new, concrete avenue for studying dark matter in a cleaner, less complicated environment than we've typically had access to before, while also raising fascinating new questions about exactly how many similar objects might be quietly scattered throughout the universe, simply waiting to be noticed by the right combination of careful observation and clever indirect detection techniques. And that's genuinely the kind of discovery that reminds you why astronomers keep pointing extraordinarily sensitive instruments like Hubble out into the depths of space in the first place. Because even after more than 3 decades of continuous operation, and after cataloging galaxies, nebulae, black holes, and countless other objects across the entire observable universe, there are still genuinely new things out there waiting to be found. Entire categories of objects nobody had ever directly confirmed before, hiding in the darkness, simply because they don't emit the the kind of light our instruments have traditionally been built to detect, and it's genuinely worth sitting with. The fact that this discovery happened using a telescope launched back in 1990, analyzing light and gravitational signatures that took the careful, patient work of dedicated researchers to properly interpret rather than some flashy, instant revelation. And I think that patient, methodical nature of real scientific discovery is honestly part of what makes a story like this one genuinely satisfying to actually understand in full, rather than just skimming a headline announcing a new space discovery without knowing what any of it actually means. And I think that's a genuinely exciting reminder that our current picture of the universe, as detailed and sophisticated as it's become, remains very much an incomplete, evolving picture, with discoveries like Cloud9 continuing to fill in genuinely significant gaps we didn't even fully realize were there. If this helped you understand exactly what Hubble actually found and why astronomers are so genuinely excited about it, hit subscribe, because we're going to keep bringing you these kinds of real, accurately explained space discoveries as they continue to happen. See you in the next one.